These are the answers to the Chapter 11 and 12 practice quiz, starting with the multiple choice questions. Number 1, we have to rank these three substances in order of increasing boiling point. So let's take a look at each substance and decide if it is polar or not, and whether or not it has hydrogen bonding. So our first molecule is acetone. Acetone looks like this. So therefore it is a polar molecule. There is an oxygen on one side, that's the negative end of the molecule, and then the carbons would be sort of the positive end. So in terms of polarity and intermolecular forces, acetone definitely has both London dispersion forces and dipole-dipole forces. Our next example is butane. This is a hydrocarbon. It is nonpolar, so it only has London dispersion forces. And then finally, propanol, it has hydrogen bonding because the oxygen is directly bonded to the hydrogen. So that molecule would experience the strongest intermolecular forces, and butane would experience the weakest intermolecular forces. So in order from lowest to highest boiling point, butane comes first, followed by acetone, and then finally propanol. So the correct answer for number 1 is B. Number 2, all we really have to do in this question is simply just read all 4 statements and decide which one is true. If we take a look at the section on covalent network solids in Chapter 12, it does mention that these types of solids are much harder and have higher melting points than molecular solids. With respect to metals, there really is no statement in the textbook that mentions what the melting points of metals are. But you can see from this example that some metals have very low melting points, around 30 or around 100 degrees Celsius. Other metals have melting points around 1,000, 1,500, and some metals have melting points that are even higher than 3,000 degrees Celsius. So I guess my point is that because the melting points of metals vary so widely, it's difficult to make any general statements about metals. So back to this question, we cannot say that metallic solids would necessarily have higher melting points than covalent network solids. And remember that ionic solids are only going to be good conductors of electricity when melted or dissolved in water. So they are not excellent conductors in the solid phase. Remember that molecular compounds like sucrose would not be good conductors when dissolved in water. So correct answer for number 2 is A. Ionic solids, which have strong ionic bonds, tend to have higher melting points than molecular solids, which have weak intermolecular forces. Number 3 requires us to think about Coulomb's law, which has to do with the attraction between charged particles. So we already know that magnesium oxide has a higher boiling point than sodium fluoride. And you know that because of Coulomb's law. Here is a list not of the boiling points, but actually of the lattice energy. So it's the same idea in that the lattice energy gives us a clue about the strength of the attractive forces between the ions. And you can see that magnesium oxide's lattice energy is much higher than that of sodium fluoride. And that's because the +2 -2 attraction, so the magnitude of the charges on the ions, is greater with magnesium oxide than it is with sodium fluoride. Now sodium chloride, that comparison, you can see that there's a smaller lattice energy for sodium chloride. Chloride is larger in size than fluoride. So therefore the distance between the ions is greater, and the attraction between sodium and chloride ions would be less than the attraction between sodium and fluoride. So we're looking for an answer that has to do with a smaller boiling point for sodium chloride compared to sodium fluoride. So correct answer is A. There is weaker Coulombic attractions in sodium chloride, so therefore it will have a lower boiling point. Number 4 is really about the difference between ethyl acetate and butyl acetate in terms of their boiling points. When you heat up this mixture and you undergo distillation, you're separating these two substances on the basis of their boiling point. The first chemical to appear in the distillate would be the one that has a lower boiling point. There's not really a difference in these molecules in terms of their polarity, but as you can see, butyl acetate is a larger molecule, has a larger carbon chain, so therefore that molecule, butyl acetate, will have greater London dispersion forces because its electron cloud is larger and it's more polarizable. So ethyl acetate, smaller electron cloud, weaker London dispersion forces. Butyl acetate, larger electron cloud, stronger London dispersion forces. Ethyl acetate has the lower boiling point. Butyl acetate has the higher boiling point. So the chemical that would first appear in the distillate would be ethyl acetate because of its weaker London dispersion forces. In number 5, we are comparing carbon tetrachloride, CCl4, which has a boiling point of 350 Kelvin, with phosphorus trifluoride, PF3, which has a boiling point of 171 Kelvin. We can tell because of the symmetry that carbon tetrachloride is nonpolar, so it only experiences London dispersion forces, and because of the asymmetry in the shape of PF3, it is polar and would experience both London dispersion forces and dipole-dipole forces. But we have to make an argument for why CCl4 has the higher boiling point. So what about CCl4 would give it stronger intermolecular forces? We're down to the choices of either A or B, because C and D are talking about why PF3 has stronger forces. That's not going to support the argument. So it's either A or B, and we cannot use B as an example since CCl4 does not experience dipole-dipole forces. So the correct answer is A. The London forces in CCl4 must be stronger than the London forces in PF3. All right, question number 6 requires us to take a closer look at how these two molecules are forming hydrogen bonds. Now, to form a hydrogen bond, a hydrogen of one molecule must be coordinated to either an oxygen, nitrogen, or a fluorine in a second molecule. So if we look at letter C, we can eliminate that choice because you can't have two hydrogens coordinated with a hydrogen bond. We can also eliminate choice B because an oxygen is coordinated to a nitrogen. Now, taking a closer look at choice A, even though there is a hydrogen connected to a nitrogen in this dashed line, look at these hydrogen atoms. They are directly bonded to carbon in the molecule. And a covalent bond between carbon and hydrogen is not going to give us that extreme polar bond that would lead to hydrogen bonding. So the hydrogen on that molecule should be directly attached to a nitrogen or an oxygen, which it is not. So the correct answer is D. And you can see that in choice D, the hydrogen is directly bonded to a nitrogen, and the dotted line coordinates it to either an oxygen or a nitrogen. So number 6 is D. All right, number 7 has to do with vapor pressure. And recall that from this graph, the higher the vapor pressure, the lower the boiling point will be. So the higher the vapor pressure, the weaker the intermolecular forces will be. All we have to do is pick the substance that has the highest vapor pressure, and that would have the weakest intermolecular forces. So correct answer is C, because 92 is the highest vapor pressure in that table. This question has to do with Coulomb's law. We're talking about ion-dipole forces here. Now, all three of these ions have the same charge. So in this case, it's not really about the magnitude of the charge, but rather the distance between the ion and the polar water molecule. So for Coulomb's law, the strongest attractive force would have to do with the smallest ion. So the shortest distance between the ion and the polar molecule. Since smaller would have the strongest attractive forces, we want to put zinc first, and then calcium, and followed by barium. So smaller radius, greater attractive force between the ion and water. So correct answer is A. Number 9, a substance did not conduct electricity as a solid, but did become a conductor when dissolved in water. We're talking about ionic bonds. That's a straightforward definition of the property of ionic substances. In number 10, this has to do with the alloys. Remember that there are two types of alloys, substitutional alloys and interstitial alloys. Now, a substitutional alloy, like in this example from your book, gold and silver, has two atoms whose radii are very similar. An interstitial alloy, in this example it's steel, iron, and carbon. The carbon is much smaller and fits in between the spaces. So in our example, if we can see the presence of extra bonds provided by the interstitial component, that is the smaller atom, it will cause the metal lattice to become harder, stronger, and less ductile. So for a gold-copper alloy to be harder than a gold-silver alloy, look at the radius of copper. Copper is smaller. So the silver-gold alloy is substitutional because those are the same size, but the gold-copper alloy is interstitial because copper is smaller than gold. So because copper atoms are smaller than silver atoms, the copper atoms will interfere more with the displacement of atoms in the alloy. Correct answer is D. Number 11, which of the following would be consistent with a molecular solid? Well, iodine molecules are nonpolar, and they would experience weak London dispersion forces. So it can't be A. We're not talking about a high melting point. It would be weak intermolecular forces, a low melting point. It's not a three-dimensional covalent network. It's going to be a molecular solid. And we know it is nonpolar, so it cannot be C, where it talks about the molecules being polar. It is not a good conductor of electricity because its valence electrons are localized in bonding and non-bonding pairs. So molecular substances are non-electrolytes. Number 12, which of the following processes involves breaking covalent bonds? Well, in letter A, you're just going from a solid to a gas. That would be separating a non-polar hydrocarbon from other molecules. You're just breaking the weak London dispersion forces between molecules. In letter B, that substance experiences hydrogen bonding, but you're still just going from a liquid to a gas. You wouldn't be breaking covalent bonds, just the strong intermolecular forces that we call hydrogen bonding. In letter C, dissolving sodium chloride in water, you'd be forming ion-dipole forces, and the only thing you're breaking would be ionic bonds between the sodium and the chloride. So the correct answer would be D. For a chlorine molecule to be broken up into two atoms of chlorine, you would have to break the covalent bond within a chlorine molecule. Number 13, steel is an alloy consisting of iron with a small amount of carbon. Elemental chromium can be added to steel to make the steel less likely to rust. Chromium atoms react with oxygen in the air to form a non-reactive layer of chromium oxide on the surface of the steel. So we have a picture at the surface and a picture at the interior of this alloy. Remember, we're looking for a layer of chromium oxide on the surface, and we don't want to see any oxidation of the iron in the interior portion. So the problem with letter A is that there's no chromium present at all on the surface. In fact, anywhere in the alloy. The problem with letter C is that if you look at the radii, iron should be similar to chromium, and yet those chromium circles are much smaller than the iron. Another problem would be there's supposed to be chromium oxide on the surface, and those oxygen atoms on the surface are not bonded to chromium at all. All right, let's take a look at letter D. Well, if chromium is oxidizing at the surface, then there should not be any oxygen present in the interior. You're preventing the oxidation in the interior, so there should not be any oxygen atoms in that portion. So correct answer is B, and you can see chromium bonded to oxygen at the surface, and you don't see any oxygen in the interior. All right, next one, number 14, we have hexane and octane. We know that octane is a little bit longer and therefore would have stronger intermolecular forces than hexane. So octane should be more viscous than hexane. So viscosity generally tends to increase with molecular size or molecular weight. And it says that viscosity decreases with increasing temperature. So a warmer liquid would be less viscous than a colder liquid. So we know that octane is more viscous than hexane. So A looks like it's good so far based on that comparison. B, that's incorrect because it says that octane is less viscous than hexane. And C and D, so far it has octane greater than hexane at the same temperature. But as temperature increases, viscosity decreases. So that means that octane at 45 degrees would actually be less viscous, so it's not A. And hexane at 25 degrees would be more viscous, so it's not C. Correct answer is D. Warm hexane is less viscous than room temperature hexane. And then octane at the same temperature would be even more viscous. All right, number 15 has to do with this heating curve. And you can see that the process occurring at 110 Kelvin, which is vaporization, is requiring more energy than the process at 90 Kelvin, which is fusion or melting. Remember that the delta H of vaporization should be larger than the delta H of fusion because in the transition from a liquid to a gas, the particles must essentially sever all of their interparticle attractive forces, whereas in the transition from solid to liquid, you're only breaking some of the attractive forces. So correct answer is A. Intermolecular attractions are completely overcome during vaporization from liquid to gas. All right, and now on to number 16. Nickel is a metal. Boron is a much smaller atom that's a metalloid. So boron is in period 2. Nickel is in period 4. So boron is much smaller in size than nickel. So we're looking for a particle diagram that represents an interstitial alloy. Correct diagram is A. Number 17. This is talking about the N-type, so the negative charges of semiconductor. So an N-type semiconductor, you can see this on pages 489 and 490. Because phosphorus has 5 valence electrons, but silicon has only 4, the extra electrons create an N-type semiconductor, N signifying that the number of negatively charged electrons has increased. So correct answer is A. Phosphorus atoms introduce additional mobile negative charges. 1 extra valence electron than silicon. All right, number 18. Let's go ahead and plot some of these vapor pressures. So at 60 degrees, it's about 175 torr. At 70 degrees, it's about 275 torr. At 80 degrees Celsius, it's about 425. At 90 degrees Celsius, about 640, and then at 95 degrees Celsius, it's actually higher than atmospheric pressure. So that means that the boiling point of this compound X must be somewhere between 90 and 95 degrees. So its boiling point is higher than that of ethyl alcohol and lower than that of water. It should experience stronger intermolecular attractive forces than ethyl alcohol because it has a higher boiling point than ethyl alcohol. All right, on to the free response questions now. Number 1, we're going to compare acetic acid with methyl acetate. We know that both molecules experience London dispersion forces. These molecules are both polar. Because of their asymmetry, they're going to experience dipole-dipole forces as well. But as you can see, only acetic acid has a hydrogen directly bonded to an oxygen, so the acetic acid experiences hydrogen bonding, whereas the methyl acetate does not. We would expect the attractive forces in acetic acid to be a little bit greater than the attractive forces in methyl acetate. And sure enough, acetic acid does have a higher boiling point. It must be because acetic acid experiences hydrogen bonding, however, methyl acetate does not. All right, moving on to part C. A student drew the following diagram to indicate the attractive forces between acetic acid molecules, and this diagram is incorrect. So we have to show that a hydrogen on one molecule is coordinated to an oxygen on a second molecule. So you might do it like this. So an oxygen on the one molecule is coordinated to a hydrogen on the other. You could also do the dashed line like this. That would work. That's an oxygen coordinated to a hydrogen. That would work. You could also do the attractive force like that. So all of these would be correct. However, it has to be the hydrogen that's directly bonded to oxygen. You could not do that. That would be incorrect because the CH bond is not the highly polar bond. We saw that earlier in one of the choices on the multiple choice about the DNA. The carbon-hydrogen bond is not the highly polar bond that gives this type of attractive force. This would be incorrect. So correct answer would be a hydrogen, that particular hydrogen, bonded to an oxygen on the second molecule. All right, moving on to part D. Propanoic acid has a slightly higher boiling point than acetic acid. Now, propanoic acid would have London dispersion forces. It is polar, so it has dipole-dipole forces, and the hydrogen directly bonded to the oxygen gives it the ability to form hydrogen bonds as well. But look at those two molecules side by side. They both have dipole-dipole forces and hydrogen bonding, but that's not the distinctive structural difference between them. Propanoic acid has an extra carbon and extra hydrogen, so this portion of the molecule would be larger in size than the portion of the molecule for acetic acid. So we're talking about the electron cloud being larger. So which type of intermolecular force is most responsible for this difference in boiling point? The London dispersion forces, because the propanoic acid is a larger molecule, larger electron cloud. Okay, moving on to free response question number 2. We have hexane, which is a non-polar substance, so it only experiences London dispersion forces. We have 2-hexanone, which is polar but does not experience hydrogen bonding. So it has London dispersion forces and dipole-dipole forces. In terms of the relative strength of the intermolecular forces, explain why hexane has a higher vapor pressure than 2-hexanone. Remember, we learned about vapor pressure. The weaker the intermolecular forces, the higher the vapor pressure will be. So hexane has weaker intermolecular forces than 2-hexanone, so it's going to have a higher vapor pressure. Which liquid should have a higher boiling point? Well, the one that has stronger forces. So 2-hexanone should have a higher boiling point and as you can see from the table, it has a lower vapor pressure. So lower vapor pressure, higher boiling point, stronger forces. All right, number 3 is talking about alloys. We have copper and zinc, and that particular alloy contains 70% copper and 30% zinc. So right now the diagram is 100% copper. So what's 30% of these atoms? Well, there are 20 atoms in the diagram. So 30% of 20 is 6. Let's replace 6 of these coppers with zinc. And you can just randomly replace the zinc throughout the structure. So I've got 6 zincs and I've got 14 coppers. That is the correct diagram. Of course, these are the same size. It's going to be classified as a substitutional alloy because the atoms are the same radii. Okay, moving on to the next free response question, number 4. We have 4 solids, A, B, C, and D. They each have unique properties, including physical appearance, melting point, conductivity, and solubility. Let's classify them as either metallic, ionic, covalent network, or molecular. Well, solid C conducts electricity when dissolved in water. That's a pretty good hint that it's going to be ionic. Solid D conducts electricity as a solid. That would have to be a metallic solid. Now, solids A and B are either covalent network or molecular. Whichever one has stronger covalent bonds, so the covalent network solid, is going to have a much higher melting point. So solid B must be covalent network because of its high melting point, and that leaves solid A as molecular. Now that we know what the 4 types are, can we identify silicon, nickel, naphthalene, and potassium chloride into these 4 categories? Well, yes. Naphthalene is a hydrocarbon that would experience weak London dispersion forces, so that's molecular. Silicon is known, just like carbon, which forms diamond or graphite, silicon is known as a covalent network solid. We've seen that. We know that potassium chloride, metal and nonmetal bonded together, is ionic, and obviously nickel is a metal. All right, well, that does it for the answers and explanations for the Chapter 11 and 12 practice quiz. I hope that was helpful. Thanks for watching.